Hey there, further math students. This video is going to go through the first section of chapter 15. And in chapter 15, we're looking at networks still, but this time focused on directed graphs. So directed graphs are networks where, just like other networks, there's vertices, there's edges, but the edges have a direction associated with them. So this could represent things like one-way roads or maybe pipes where water can only flow in one direction. You don't hear this word too often, but directed graphs can also be called digraphs. There's a bit of a shortening there. And they can also be weighted, so they can also have numbers on the edges that give an indication of time or distance or something like that. So here's just a really basic example to see what a directed graph looks like. So using the network shown to the left, which vertices can be reached when starting from vertex A, B, C, and D. So you can see that this network's got it's got vertices, it's got edges, but the edges have arrows on them. So for example, if we were starting from vertex A, the other vertices we could get to, well, we could get directly to B. So we could list that as part of our answer. We could get directly to C. Okay, so we could get to vertex C, but we wouldn't be able to get to vertex D because no matter which sort of way we try to travel around this network, we can't go directly to D. We can go to C, but then we can't get from C to D. And if we went to B first, well, we could go from A to B to C, but again, we've got the same problem. We can't get to vertex D. So if we were starting from vertex A, we'd be able to get to vertex B and vertex C, but not D. If we started from vertex B, well, let's have a look. We can't go directly to vertex A. We can get to vertex C. But once we get to vertex C, there's not really anywhere else we can go either because we're going kind of against the arrows there. So from vertex B, we can actually only get to vertex C. If we started from vertex C, you can tell that actually, well, all the arrows kind of lead into vertex C. There's actually nothing leading out of vertex C. So if you were starting at vertex C in this network, you can't go anywhere. So vertex C would be, I guess, none of them. And vertex D, if we started from vertex D, well, we'd be able to get directly to vertex A, directly to vertex C, and we could also get to B by going to A and then B. So for vertex D, we can reach A, B, and C. Okay. So a common, or one of the, I guess, many applications of directed graphs is in measuring what we call flow through a network. So a common example of this might be like traffic flow, like how many cars can be on a road at the same time, or how many people can be going through a walkway at a particular time. Or it might be like water flow through pipes, the amount of liters that can go through a pipe at any given time. And the way that we measure the flow through a network is to make what we call a cut across the network. And a cut is a line that separates the graph into two sections. And what it kind of has to do is completely stop the flow from the start to the finish. And often in networks terminology, the word source will be like our starting point and sink will be the finish. It's like if you imagine the source is like where the water's coming from and the sink is where the water ends up. So there's two sort of pictures here that both kind of show the same directed graph. You can see that all the edges have got directions on them, and they've got a starting point and a finishing point, a source and a sink. This dotted line here on the left-hand side, this represents a cut because once you've kind of drawn this, if you imagine that we're cutting off the edges all the way along that dotted line, there would be no way to get from the start to the end anymore if we cut all those things off. Right? No matter which way you go, you're going to kind of run into this cut. Whereas this second dotted line, even though it's cut off some of the flow in the network, it's not called a cut because if we were going to sort of start from our source, we can actually still get from the start to the end. Right? So a cut has to completely cut off the flow. So the one on the left-hand side is a cut, the one on the right-hand side is not. Okay. If we're asked to find the maximum flow in a network, we find it by determining the cut with the smallest possible capacity. And the capacity of the cut is just the sum of the weight of each edge. So we actually just add the weightings for each edge together of that cut. Edges that cannot contribute to the flow of a network in the required direction are counted as zero. We sometimes kind of think of them as like backwards edges, but we'll get to that in some examples and I think you'll see what that means. But the key idea here is that the cut with the smallest capacity gives the maximum flow of the network, or in other words, the maximum flow is equal to the minimum cut. And we're going to do a bunch of examples to see how this works. Okay, and there is this little note here, I touched on it just before, just being careful with edges that cross edges that are going backwards because we don't have to count them. And in one of the later examples, we'll see how that works. Okay, so here's a nice simple network where it's actually just kind of like a straight line. We've got 4 vertices and 3 edges, but you can see that like our source, our starting point is just point A, and our finishing point is point D. And essentially, if we're trying to think about the different cuts we can make, well, the different cuts we could make, we could cut through that first edge there, we could cut through that second edge there, or we could cut through this third edge here, right? Now the idea, when we work out the capacity of each cut, so this first one cuts through an edge that's 700, this second one cuts through an edge that's 600, and this third one cuts through an edge that's 800. Now remember, this idea was that the maximum flow is equal to the minimum cut. So we're going to say that the maximum flow here is equal to the smallest cut, and the smallest cut that we just made was 600. Right. Now this kind of makes sense, because if you were going to say, well, maybe these edges represent roads or something like that, and on the first section of road, you're allowed to have, I don't know, 700 cars per minute. But in this next section of road, you can only have 600 cars per minute, and in this last section, you can have 800 cars per minute. Well, through the whole network, if you've got this section here where there's 600 cars per minute going, and there's nowhere else for those cars to go, it makes sense that the smallest number is actually what's telling us how many people can be getting through the network at a given time, how many cars can be getting through the network at a given time. It has to be the smallest one, because if you can only get 600 through here, well, it doesn't matter if you can get 800 over here, because you're not going to get them all through because of this previous bit. Okay, so that's, I guess, probably not a great explanation, but that's why the minimum cut is actually telling us the maximum flow, because it sort of seems a bit backwards, but there's a good reason for it. All right, let's try a couple more.